Good morning. I am Vinayak, a student at Indian Institute of Technology, Bombay, from Mumbai, India. I will be presenting our research on evaluation methods in competitive examinations. Firstly, I would like to apologize for not being able to attend the conference due to the most unexpected of reasons. I shall try my best to convey our results as clearly as possible. Let's begin. Firstly, an overview of our presentation. I'll be talking about the need for the work we have done, and then I shall be explaining the problem statement we are tackling in more specific terms. Later we will look at some definitions we used and some of the assumptions we have made. Next, I will be talking about the algorithm we've designed and try to explain and illustrate with an example. After that, we will be seeing some of the simulations done, and then I shall be concluding with a few remarks on the future directions we intend to pursue. Motivation. Competitive exams nowadays are the major events in life of today's youth. Qualifying in them usually leads to a better job or a better education. The format of these exams has gone from lengthy descriptive questions to multiple choice questions. Exams like GRE, TOEFL and GATE in India, which affect a majority of people, now use multiple choice questions because of their ease of evaluation and the speed and computerization of the evaluation methods. The major problem one faces when looking at multiple choice questions is the guessing problem, where students can easily guess one among 4 or one among 5 of the options. In a study done by R.L. Karandikar in 2010 on multiple choice tests and negative marking says that if 1,000 students take an exam and only 900 of them are allowed to guess, then more than 120 of the ineligible students will get selected. Hence it's a serious issue, and because everybody guesses, 100% of the candidates guess, and the ranking based on marks does not depict the capabilities of the students. So what is the solution to the guessing problem? Solution to the guessing problem is the computerized adaptive testing. You have a huge repository of questions with known difficulty levels. The questions are fielded to the student and he is evaluated continuously online as he answers these questions, and questions he faces depend on how he answers the previous questions. As you can see, this requires a lot of computer based infrastructure, networking and so on. But when we look at the case of offline examinations, here the question papers are distributed to the students and they are given OMR sheet. They have to mark in the answers, and after the examination is done, the sheets are collected and then they are evaluated. So there is no chance of doing a continuous evaluation during the exam. Our research is looking at these kind of offline examinations and how to minimize the number of gate crashing candidates. So marks matrix. So the marks matrix is what we obtain after completion of an offline examination and the evaluation. We have a typical marks matrix is shown here, and the rows correspond to the students. There are n students and m questions, and the columns correspond to the questions. Now each correct answer gets a score of 1, and an unattempted or a wrong one gets a score of 0. As you can see, we are not considered negative marking. So here student 1 has got the question 1 right, question 2 right, whereas he's got the last question wrong. Similarly, we have student 2 who has gotten the first question right and the second question wrong and the last question right. So it's the descriptive example. Now the problem statement is that given the marks matrix, we need to compute the capability levels of students and the easiness levels of the questions. Now we have to define these terms. So a question easiness level It indicates the probability in which an average student answers a question correctly. So a 0, if the probability is 0, then it would be a very difficult question, and if the average student is able to answer the question correctly with the probability 1, then it's the easiest question. Now the capability level describes the level of preparedness of a student. If it is 0, then we say it's an unprepared student, and if the capability level is 1, then it's a well prepared student. Next we look at the confidence level definition. This is defined per student per question. It's the probability with which a given student with a capability level gets a given question with a known easiness level correctly. As we can see, the confidence level depends on both easiness level and capability level. As you can see in the graph, we have tried to approximate a student's performance, that is how he tries to answer for various levels of question easiness levels. Here the x-axis is the easiness level and the y-axis is the confidence level. So, and each line here you see depicts one capability level. The lowest one is for the 0 capability level, is the unprepared student. So the unprepared student will guess questions of all easiness levels because he does not know any of the answers. He's going to guess all of them. And the highest, the topmost line depicts a student of capability 1. So he is able to answer questions. He does not need to guess. He is going to get questions which have easiness level greater than 0.75 always right. And we further assume that the question paper has certain questions which all the students find difficult and will guess. To further get a feel about the confidence level, let's consider an example. Consider a student with capability level of 0.65 and he's answering a question of easiness level 0.4. So his confidence level is 0.26. So what does this mean? So if this student is given 100 questions of easiness level 0.4, then 26 of questions he would answer correctly on an average. Now if we decrease the number of questions, we can see that the confidence level fails to capture his performance in the examination. So if there are only 10 questions, say, you can't say that he's going to answer 2.6 questions correctly. You would have to round off the levels ranging from 0.25 to 0.3, and you would say that he would answer 3 questions correctly out of 10. Therefore we see that if the number of questions is less, then the marks he would score would not depict his confidence level correctly. So instead of using the marks matrix, we will use confidence level values instead. This would help us capture the exact capabilities and easiness levels. Now I shall explain about some of the notations we used, which will be seen in the algorithm. Small c sub I is the capability level of the ith student. Lowercase e sub j is the easiness level of the jth question. Lowercase m sub I is the total marks scored by the ith student. It is obtained by taking the row sums in the marks matrix. Lowercase q sub j is the number of students who answer the jth question correctly. For the jth question, it is obtained by summing the entries in the jth column of the marks matrix. Now uppercase C is the student capability vector and uppercase E is the question's easiness level vector. Lowercase m sub c is the marks that could be obtained by a student of capability C if he is given a set of questions with a known question easiness vector. Similarly, a lowercase q sub e is the number of students who might answer the question correctly given a question of easiness level E, and we know the capabilities of the students who are answering. Uppercase C sub n and uppercase E sub n are vectors we have defined which have n equally spaced values between 0 and 1. Now I'll try to explain a pseudocode of this algorithm. Firstly, we initialize the easiness level vector. Then we consider each student. We try to find their capability level, which gives us marks which are closest to the actual marks he obtained. Similarly, once all the students' capability vectors are found out, we then try to find the easiness level for each question, such that given the capability levels we have found, which easiness level for that question which would minimize lowercase q sub e minus the marks scored by that question. Once we get the easiness level vector, we normalize and make sure that the mean of the easiness level vector stays at 0.5. Once we get the easiness vector, we start again with each student, and this is performed for a fixed number of iterations. I understand that the explanation is not clear by just reading the pseudocode, so I shall try to explain it by using an illustration. So from the marks matrix, as you can see, we have look at the student marks vector. These are the marks obtained by students in the examination. These are the true marks they have obtained. This vector is obtained from the marks matrix. So first we initialize the easiness vector. Let's say all of them have the same easiness levels. Then we define our uppercase C sub n as having 10 levels from 0 to 1, the interval of 0.1. Now let's consider the first entry of the uppercase m sub c vector, the MC vector. So it is 1.25. It means that a student with a capability of 0 answering a set of 5 questions of easiness level 0.5 will get 1.25 marks. Similarly, a student with a capability of 0.1 answering 5 questions of 0.5 easiness level will get 1.5 marks, and so on. Now we compare the actual marks scored by a student to the marks we have generated. So here we for the first student we compare 2.86 is the mark scored. We compare it with the entries of this vector. We see that it is closest to 2.75, and the capability corresponding to this marks is 0.6, and he is assigned that particular capability. Similarly, for the second student, we see that he is scored 1.16, and this is closest to 1.25, which corresponds to a capability of 0, and that is assigned to him. This is performed for all the students, and we get an estimated capability level. Now we use this estimated capability vector to find the estimated easiness vector. So the question marks is obtained from the marks matrix, and we have the uppercase E sub n vector similar to the uppercase C sub n vector. And what does this vector mean? This means that if students of these capabilities are made to answer a question of easiness level 0, then 2.1 of them will get it right. Similarly, if students of these capabilities answer the most easiest question, then 7.1 of them will get it right. As was done in the previous slide, we compared these marks with the marks that they could possibly obtain, and assign the corresponding easiness level to the estimated easiness vector. Once we obtain this vector, the estimated easiness, it is mean normalized as was done in the last step of the algorithm. It is then substituted in the initial ease position, and then the algorithm continues for a set number of iterations. We try to simulate our algorithm for 200 students and 20 questions, and the number of levels in the capital C sub n and the capital E sub n vectors was 10,000, and the algorithm was executed for 10 iterations. To perform the simulations, we use Scilab of version 5.3.3. It's a free and open source software developed by Scilab Enterprises. Here we are comparing the actual levels of easiness and the estimations which we found. Clearly we can see that estimated ones are approximate very closely to the actual levels from which we started. As you might have noticed, the initial easiness level from which we start is arbitrary. We can start with any easiness levels, any initial level. So as we see in this plot, we have started with various initial easiness levels, and they all give us the correct actual easiness level. So irrespective of what your initial easiness level from which you start the algorithm always will give us the correct answer. The future directions to this work would be to study how the algorithm behaves when we use actual marks instead of using the confidence levels. The execution time of the algorithm is proportional to the number of students, the number of questions, and it increases rapidly as they are increased. As you can see, the algorithm has two minimizations which are done alternatively, and we wish to use the results given on alternating minimization developed by Jain et al. In a 2013 paper. Then we try our algorithm on real exam data and see how it fares when compared to the current evaluation methods. Thank you. For any queries or questions, please write to the emails which are now visible on the screen.